Okay. Hello, dynamics students. I wonder if we have anybody yet. Let's see. I'll look and see if I've got any students here. Nope, it's just me. Nobody has shown up yet. But we have 10 minutes. What a shame. You could be asking me questions and getting some more valuable knowledge here. But it's early, maybe fixing breakfast or something. Today's Wednesday, the 26th of August. And we're studying an engineering science course called Dynamics. It's actually called Elementary Dynamics, but trust me, there's nothing elementary about it. My opinion is it's the most difficult of the engineering science courses. All engineers take these engineering science courses before they specialize at their professional school in whatever they do, electrical maybe, or mechanical, or what are the other fields? There's industrial engineering. Hey, look, I've got a student. I've got Gage. Hey, Gage, say hi.
How's it going?
Yeah, going good.
Yeah,
You're my one and only right now, Gage.
yeah, I guess so.
Were you my one and only another time before?
No, I don't believe so.
I don't remember. Well, as long as you've got me all to yourself, do you have any comments or questions for me?
No, I'm good right now.
Oh, that's good. I'd love to get to know everybody. Uh, what uh, what are you going to do? Go to OSU maybe?
Yeah, I'm already at OSU Tulsa, so I have this and Calc 3 left to take at TCC.
Good
So
for you.
I'm taking 4 classes at OSU Tulsa this semester as well as your class.
Well, you're going to have one of my classes next year?
I don't know.
Oh, oh,
I don't think so. I'm just taking this class and then I'm
oh,
taking
okay.
4 at
Yeah.
OSU Tulsa this semester too.
Well, good for you. It's cheaper at TCC.
Yeah, it is. Definitely.
What do you have to pay for a class at OSU Tulsa?
I'm really not exactly sure. I know my tuition bill this year, I think, was like for the 4 classes I'm taking, it was like 6,500, I think.
Man, that's a lot of money, you know it?
Yeah, it's definitely more than what TCC was, but it's still cheaper than going to Stillwater, so that's always a plus.
And it's definitely cheaper than TU.
Yeah, for sure.
I bet TU would cost you more than twice that.
Oh yeah, I bet it would since it's a private college.
Well, let's see if we got any more customers here. Nope, you're still my one and
Still
only.
the only one, huh? They're running out of
Really?
time, aren't they?
I'm sorry, go ahead.
I said they're running out of time, aren't they?
Yeah. Well, they have 7 minutes. That's a lovely campus down there, that TU Tulsa campus.
Yeah, it's pretty nice.
It's really nice. Darn nice. Now, did you say you have to take any classes at Stillwater at all?
So
Gage?
right now I have right now I have 4 classes at Still. No, I've not taken any at Stillwater. Only OSU Tulsa.
Just OSU Tulsa. Well,
Yes.
will you have to take something at Stillwater sometime?
As long as you play it right, no, you don't. But
Really?
sometimes if you like get behind or get ahead, they don't
Yeah,
offer the class right at the
yeah.
same time. So
Trying to schedule can be tricky.
exactly.
It's
But for the
just
most
that at
part, they
Stillwater, I know they have a lot of equipment, testing equipment, for instance,
yeah.
and I don't know if they have all that at OSU Tulsa. I just don't know. I've met some of the professors down there. I have trouble remembering names, but I've met some of them. One guy's name is Knight, I think. Does that ring a bell?
Yeah, there's Ron Knight. He's an
Yeah,
advisor.
Ron Knight. Yeah,
Yeah, he's probably all of our advisors.
yeah. He can tell you which courses to take. And then I knew the electrical guy that taught electrical stuff. Oh, but his name slips my mind. And I've met I've met some of the ones at Stillwater. Well, let's see how we're doing. Oh, look at here. We've got Ashley and Tyler now. So we're picking up student, and there comes Megan. We got Megan. Engage. We've got a good class so far. How about some of you guys? We have 4 more minutes. Did you have any comments or questions for me before we get started? How about Megan? Megan's been very helpful to me with those, what do they call them? Thank you points. How about it, Megan? Did you have any comment or question for me? Unmute and say hi. I wonder if I got everybody muted or what. Let me see about that. I don't know. It says mute all. I don't want to push that. And we have Ashley. Ashley's with us. There's also a thing down here that says chat. I don't know how to work that, but I guess you guys can chat me, right? Anytime anybody want to try that, I'm willing to learn how that works. Anybody out there know how to do that chat thing? It says chat, C-H-A-T. Isn't that French for a kitty cat? I think that's the French word for a cat. Where's my French speakers out there? French is such a beautiful language. You can say ordinary stuff like je voudrais sortir la poubelle. Doesn't that sound romantic? What it means is I need to take out, or I want to take out the trash.
That's a good one.
Yeah, I mean, it does sound romantic. Well, okay, I think it's time to start our wonderful lecture. Let me check the one last roll call here. Oh, look, we got Megan, Gage, Ashley, Nicholas. Nicholas has showed up.
Good morning.
Yeah, good going, Nicholas. Oh, hey, there's a chat. Megan went type message here. Am I supposed to type something, Megan? Still don't know how that chat works.
I didn't type anything, so I don't know what's happening.
Okay, that's fine. Gage and Ashley, Nicholas, and Tyler and Shane. Shane is with us. Okay, well, it's time for our class, and let's get rolling here. Today's topic is normal tangential coordinates. Let me talk about all three coordinate systems for a little bit, and then and then we're going to concentrate on normal tangential coordinates. But see, there's your XY coordinates, and another name for that is Cartesian coordinates. And then there's the normal tangential coordinates. I don't know of any other name for that. And then there's the radial transverse coordinates, but they're also called polar coordinates. Now in the normal tangential, or in the XY coordinates, your position vector is equal to this here. I've written this before for you, but I believe in repetition. Now in the normal tangential coordinate system, I think I've told you this too, that there is no position vector. See, the position vector goes from the origin of your coordinate system to the body that you're interested in. You're trying to figure out its velocity, for instance. But in the normal tangential system, the origin of your coordinate system is based on the body. So there is no distance from the origin of the coordinate system to the body. The position vector is 0. Now in the polar or radial transverse coordinates, the position vector is equal to hope you can read my writing. It's equal to r, which is the magnitude of your position vector, times a tangential unit vector. See, these are your unit vectors. I and j are the unit vectors in x and y. Now we have unit vectors in the normal tangential, and we need them for velocity and acceleration. Here, let me do the velocities now. The velocity vector in Cartesian coordinates goes like this. Now the velocity vector in the normal tangential system goes like this. That's wrong. I'm getting mixed up. I'm confusing myself here. Just a minute now. I had a senior moment just now, but I think I'm back on track. And the velocity vector in the radial transverse unit system is equal to that's not right. Just a minute here, let me think. Okay, now let me check all this. I did all that from memory, but we better check it. I don't want to lie to you if I can help it. But all these are in the flap of your book. I got no doubt about that one. We've done that before. But I do need to ask you, what the heck does X dot mean? Let me go to one of my wonderful students here. And Tyler, unmute and tell me, what does X dot mean? Tyler, that dot means something. What does it mean, Tyler? Go ahead, unmute and tell me, Tyler.
I'm not sure.
That's okay. See, I need to know that. I need to know that you're not sure. That's valuable information. And count yourself blessed, Tyler, because you're going to find out here real quick what it is. It has a meaning. It means you take the first derivative, but with respect to what, Tyler? What do I put down here, Tyler? First derivative with respect to what? And you can say, I'm not sure again if you want. It's up to you. But what do you think? That dot
Was it
means
time?
first derivative, but with respect to what?
Was it time?
Yeah, good going. That's it. That's important. That whenever you see that dot, it means with respect to time. Okay, well, great. So now here's the, let's make sure that these are right now. Look in the flap of your book. You know what I'm talking about? You open your book, and in the very flap of your book, they're going to give you the velocity in the tangential direction, and it says, trying to find it here. I don't see it. It's right here in the flap of your book. So yeah, there it is. It says V dot. I just found it. Here, I'll point to it. Do you see where my finger is wiggling there? It's right there. No, wait a minute, that's wrong. Guys, I did that wrong. This is all wrong. I told you I had a senior moment. But we're going to get it right. I hope you erase that because it was wrong. There we go. That's better. The velocity vector in the normal tangential direction is the magnitude of the velocity vector times the direction of the velocity vector. In fact, that's true for any vector. You know, like vector A, for instance, is equal to the magnitude of A times some kind of unit vector in the direction of the vector. I'll just put a fake unit vector there. I don't know. A could be in any of the directions whatsoever. If you had a vector B, it's equal to its magnitude times, here we'll put a little subscript there. We'll call that U of B. I call that, it's a form of a vector notation so that you'll know that you're dealing with a unit vector. But you know that a vector is equal to its magnitude times its direction. And that's all we're saying here with the velocity. It's the magnitude of the velocity times the unit vector in its direction.
What's the subscript next to the unit vector? Is that a T?
The subscript next to the unit vector, that's a T. You talking about that little T right there?
Yes, sir. I was just making sure. Thank
Yeah,
you.
here, let me try to write it better where you can read it. I don't know. I don't know if that's any better. There we go. It's supposed to be a T. It's supposed to be a T, okay? Now, they don't even have that in your book. I don't see where they have that in the flap of your book. It's not in there. But this is, look in the flap of your book and see if you can see this R dot. There it is. I see it. And the R theta dot, yeah, it's in there. It's kind of in disguise. In the flap of your book, they're writing this like this. This is the what they call the radial component. This system here is called the radial transverse coordinate system. And this here is a component. It's called the transverse component of your velocity, and it's equal to R theta dot. That is in the flap of your book. You'll see it says V sub theta is equal to R theta dot. If you look hard enough, there it is. I'm wiggling my finger and it's right there. It says V sub theta is equal to R theta dot. Okay, well, great. We've talked about the three systems there. Now let's talk about them a little bit more, and then we'll explore this one in detail. The key to these coordinate systems are these unit vectors. The heart and soul of these coordinate systems are these unit vectors. See, in this system, you have I and J and K. You have K if you're in 3 dimensions. In this system here, you have U of N and U of T. Those are the unit vectors in the normal tangential coordinate system. In this system here, you have U of R and U of theta. And they have names. This is called the unit vector in the radial direction. And this one here is called the transverse unit vector. That's the radial unit vector. That's the transverse unit vector. Okay, let's show you the directions of all these unit vectors. And then we're going to talk about the normal tangential system in detail. But this isn't going to hurt us to kind of get an overview of all three of them. Let's suppose you had maybe an airplane, and it's doing this. There you go. Now we need to find our coordinate system. Let's put our coordinate system right here. Here's X, and here's Y. Okay. suppose your airplane is right here. Here, I'll draw you an airplane. Okay, there you go. See that airplane? Now we want to have, we'd like to have a position vector, and it's always measured from the origin of your coordinate system. It goes like, there you go. There's your position vector of your airplane. Now what we want is we want I and J, U of N and U of T, U of R and U of theta. We want to draw all those. Well, see, if this is the X direction, then the I unit vector is right here. And you always draw these at your body. If that plane is your body, there's your I unit vector. See, it's always in the direction of the X axis. You don't put it down here, though. The body's not down here. That's the body. You put it at the body. And the Y unit vector, I mean the J unit vector, there it is right there. Ta-da. So we just drew this R thing. By the way, that R thing has a name. Let me pick on somebody here. I love picking on my wonderful students. Taylor, what's the name of that R vector thing? What's the name of it?
Position vector?
Yay, good going. Taylor's awake. He's been listening. They call it the position vector. Good going, Taylor. Now, let's draw the normal and tangential. There is no position vector because, see, the coordinate system is based on your body. It's really kind of weird. And here's your coordinate system. That's your tangential coordinate. And this is your normal coordinate. And the tangential unit vector, let me do that in maybe a different color. We'll do it in red, what the heck. The tangential unit vector, hope you can read my writing. That's supposed to be a U with a little t under it. It's always in the direction of your motion. And the unit, or the normal unit vector, there it is. There's your, it's perpendicular to your tangential unit vector. Can you read my writing? That's supposed to be a U with a T under it. This is a U with an N. It's the normal unit vector. It's perpendicular to the tangential unit vector, and it has to go to the inside of the curve. Okay. Now what about the radial and transverse unit vectors? Well, the radial unit vector is in the direction of the position vector. There's your radial unit vector. It's always in the direction of your position vector. And the transverse unit vector, it's perpendicular to it and counterclockwise. I'm trying to draw a theta there and I'm not having any luck. There we go, we tried. That thing has a name. It's called the transverse unit vector. it's perpendicular to the radial unit vector. This one's called the radial unit vector. And it is, it's in the direction of your position vector. See your position vector? Look, the radial unit vector is in the same direction as the position vector. The transverse unit vector is perpendicular to the radial unit vector, and it's counterclockwise. If you take the radial and turn it counterclockwise, it always does that. It's always counterclockwise. Okay, well, great. Let's do another one. Let's suppose that this airplane comes down here and crashes in the ground. It's a drone, okay? And the controls or whatever on the drone went haywire, and it comes down here and it splashes down. And we're going to do the I, J, U of T, U of N, U of R, U of theta. We're going to do all of those unit vectors right here so that you'll learn more and not fall asleep. Draw an XY axis, draw an airplane doing that. And here's your airplane now. This is your airplane. And it's right there. You do it. You put in the I and the J. At the body, here, this is your airplane. Not a very good airplane, but there it is. You put in the tangential and normal. Remember what the directions are now. This is in the direction of your velocity. See, the airplane's going like that. So we know it's the velocity. This is, what do they call it? Perpendicular to the tangential one. This is radial and transverse. I've explained them all. I'm going to shut up, and for a minute or two, you draw that. You put in the four unit vectors, and then I'll tell you what the answers are, and we'll see if you got it right. Go for it. Oops. I wonder if we got any more students. Tyler, Taylor, Stuart, Shane, Ryan. We got Ryan. That's good. We have Braxton. Yes, Ashley, Alex. Got a wonderful class. I think who's after Braxton? I can't seem to move this thing. There we go. There's there's Jackson and Mark. And Stuart and Shane. Got a wonderful class, yeah. Right now, if you wonder what we're doing, you should draw an XY axis. You should draw an airplane that goes like that. And right at this moment here, you're supposed to draw the 6 unit vectors, because that's the heart and soul of these coordinate systems. All right, well, that's enough time. Maybe you're done. Maybe you've got some of them done. Well, we really need the position vector. And here comes the position vector. It goes from the origin of your coordinate system to the body. See, there's the body. That's where the body is, the airplane in this case. And you're looking at the position vector. Okay, good. Now let's do the I and J. Maybe I could do those in blue. I got a blue here. We'll try that. I wish I had some green. Okay, now here's the I unit vector. There it is. And here's the J unit vector. Did you get your I and J unit vectors at the position of the body like that? I hope so. Now let's do the normal and tangential. Well, see, if he's coming down here with this velocity, then this is the normal, I'm sorry, the tangential, that's the tangential unit vector. That's supposed to be a T if you can read it. That's the tangential, it's in the direction of your velocity. See the airplane's going like that, and that's the tangential. Now the normal is perpendicular to that. There's the normal unit vector. Okay, is that the way you have yours? And it's got to be to the inside of the curve. Now see, the curve is, he's still curving. It looks straight, but he's still got a curve to him. And so it always goes, the normal unit vector always goes to the inside of the curve. Finally, we have the radial and transverse unit vector. Well, the radial unit vector is in the same direction as the position vector. So you know what? I don't have much room here, but it's in the same direction as your I unit vector. The I unit vector and the radial unit vector, they're going in the same direction. And counterclockwise from that, and perpendicular to that, is the transverse unit vector. You know what? It's in the same direction in this case as the J unit vector. They just happen to coincide. Well, I hope you got that right. If we had lots and lots of time, I would do a whole bunch of other positions. Maybe have the airplane in here someplace, and you'd have a position vector here if the airplane was there, and you'd have to find the unit vectors in that position. But we don't have lots and lots of time. We need to focus in on the normal tangential system now, unless there's any comments or questions. Okay, well, nobody said anything. I guess you're all right. So we'll erase that. But you must know those unit vectors. It's kind of like getting lost in a wilderness on a cloudy day. You can't tell where the sun is. It's not nighttime, and it's cloudy anyway. You can't tell where the stars are, the moon, or anything. And maybe you're in a flat, marshy, I don't know, forest. You don't know your directions. You need to know your direction. If you want to get out of that and not be lost, you got to know your directions. We can't work problems in here unless we know our directions. And the directions are given by these unit vectors like I and J and K, or that U, T, and that U, N thing, the unit vectors. Without those, we won't know our directions. That happened to me one time. I got lost in a swamp. It was down by Dewar, Oklahoma. There's some flooded timber down there. And I was wearing my waders. And I got lost. It was a cloudy day and I couldn't tell my directions. And so I walked and walked and walked. And after a couple of hours, I noticed, hey, wait a minute, I've been here before. I recognize this particular spot. I had gone in a great big circle. Have you ever heard of people getting lost and going in a circle? It happens. Because when you walk, your dominant foot, perhaps, takes a slightly longer step than your other leg, okay? And so that means that you very, very slowly move in a circle. And when I came back to that same spot, I realized, uh-oh, I've gone in a big circle. I am really lost. This is serious. I'd tell you the rest of the story, but obviously I didn't stay there and die and rot because I lived through it. But we don't have time for that. Directions are important, though. Now let's talk about the normal tangential unit system. We know that there is no position vector because the position vector goes from the origin of your unit of your coordinate system to the body. But the normal tangential coordinates are based on the body. They go with your body. They travel along with your body. And so you don't have any position vector. Now the velocity is given by the magnitude of the velocity times the tangential unit vector. Now, if you want the acceleration, these are both changing. It's not like I and J and K. They don't change. This is a variable. See, remember that airplane? When the airplane's doing this, there's your tangential unit vector. When the airplane's doing this, there's your tangential unit vector. When the airplane's doing this, look, it's changing. It's not a constant. Now, I, J, and K are constant. I is doing this here. I is doing this here. I is doing this here. It never changes. But that one is a variable. Both of these are variable. You have a product of two variables. And when you're taking the derivative, you know that the acceleration by definition is the derivative of velocity. That's really a definition. Put 3 lines there. Now, to take the derivative of a product, you have to use the rule. Let me go to one of my excellent students here. Let's see. Let's go to Stuart. Stuart, to take the derivative of a product, you use the rule. What is that, Stuart?
Is it the product rule?
Yay, Stuart, good going. It's the product rule. So what you do is you take V times the derivative of that with respect to time. And being lazy, I'll just put a dot over it. Didn't we decide that? It's the first derivative with respect to time. But we're not done yet. Product rule says, then you have to take the derivative of that with respect to time times the second one. There you have it. Now, usually they write this the other way. They'll write it as V dot U of t plus V times U of t dot. I didn't lose anybody by switching those, did I? I didn't lose anybody, did I? Now there is a dot there. There we go. Okay. Now, if you look this up in the book, here's what they say. they say acceleration in this system, the normal tangential system, is equal to v dot u of t. We got another name for that. It's called speed. That's your speed. Plus v u of t dot. First derivative of it. There you go. U of t dot. Only they don't write it like that. They write it like this. If you look in your book there, they completely change this, and they write it like this. Can you find that? It's in the flap of your book. It's where my finger's wiggling right in here. See, the tangential acceleration is the v dot. We got that. And the normal acceleration is the v squared over rho. That's the part I need to explain to you. We need to explain to you, well, obviously that's equal to that, but I need to explain to you how come this is equal to that. Well, let's do that. What I need to show you, what I need to do is find the derivative of this tangential unit vector. Okay, well, I need some room to do that. I'm going to erase all this stuff so I'll have some room. And right now, what I want to show you is how to find the first derivative of the tangential unit vector. That's what I want to show you. So let me erase this, and then we'll finish this off, and we'll have our equation. We'll work some problems. That's the plan. Well, you guys all took calculus. You know what the derivative is. We want to take the derivative of the tangential unit vector with respect to time. That's what that is. And to take the derivative, if you had, say you had an airplane that was going, like that. So here's your tangential unit vector. And later, here's your tangential unit vector. Do you notice it changed direction? But now the magnitude should be the same. The magnitude is 1. That's why they call it a unit vector. It's just 1. We'll put a prime on this one because that's later. That's just happening later. Do you remember how to find this? What you do is you take a limit as t approaches 0 of your final value minus your initial value. And then you divide by time. By definition, that's what a derivative is. Do you remember how to subtract vectors? Well, they taught me how to do it in school many years ago. What you do is you put their tails together. See, here's u of t, and here's u of t prime. You put their tails together, and what you do is, well, they're both the same length. They're both 1 unit long. And what you do is you connect the arrowheads. You connect the tips. You see that little thing right there? That little vector right there is the direction of the difference. When you subtract these two, it's called a vector difference. And it's in that direction. Well, you know what that direction is? That's in the normal direction. See, it's perpendicular. You were going here, and going this way is the normal unit vector to the inside of the curve. perpendicular. But now how big is it? Well, they also taught me in school many years ago the arc length formula. And you guys know this. The arc length equation goes like this. Distance is equal to r times theta, but the catch is the theta has to be in radians. Remember that? S equals r theta, it's called the arc length equation. So this little distance here, you want to call it maybe ds. That's, well, no, that's not a good name for it. Let's call it du. Is equal to the distance here, which is 1. These are both unit vectors, times d theta. Okay. du d theta. Good going. Divide by time. We can do that. And what we'll have is the derivative of u with respect to time is equal to d theta dt. It's equal to theta dot, isn't it? Okay. So this here is equal to, well, it's just equal to theta dot. Looks to me like it's equal to theta dot. Yeah. Okay. Now let's go back to what we had earlier. I erased it, unfortunately. But we had the velocity is equal to we had the acceleration is equal to v dot u of t plus gosh, I don't know. What do we have? I'm having a senior moment again. Just one tiny minute here while I get my mind right. This is all in your book, by the way. We could read that in the book, but I'm forgetting. See what I did? Let's go back. What I did was I said v equals v times u sub t. Yeah, there we go. And so what I have here, I took the derivative to get the acceleration. To get the acceleration, I went v dot u of t plus, okay, that one times derivative of that, plus v times u of t dot. Okay, so this is v times u of t dot, which we just figured out is theta dot u sub n. We know it's in the n direction, or the normal direction, and we know that this term here is equal to theta dot. So we got v times theta dot, if that makes any sense. Now, when you're in a curve like this, let me make some more room here. We're almost done, and then we'll have our equation. I'll have shown you where it comes from. See, when you're in a curve like this, they call this the radius of curvature. It would fit a circle if you put a big circle around it. And as that airplane moves, a distance here, call it ds. That ds is equal to rho d theta, where d theta is the arc length. Remember the arc length formula. R equals, how's it go? S equals R theta. Well, ds equals rho d theta. And so
What does rho represent?
Yeah, go ahead.
What does rho represent again?
Rho is called the radius of curvature. We showed you that Monday. We talked about the radius of curvature. If you're a little bit fuzzy on it, go back and look at the YouTube for Monday. Now, who was that?
No, it's Taylor.
Taylor, go back and look at the YouTube for Monday. It talks us. I spent some time talking about the radius of curvature. Okay, now if you want the velocity, just divide by time. Divide by time. Can you see that the velocity is equal to rho theta dot? So we could put that in here. We could have rho we could have rho theta dot, right? Velocity is, did I do that right? Yeah, I think I did that right. Okay, so if you plug that in there, what you'll have is, gosh, I got a bad feeling I'm goofing this up. Is that going to show? Yeah. We got the velocity equals this. So it's equal to rho theta dot times theta dot. Holy cow, there's two theta dots there, isn't there? That's not what I want. Just a minute now, just one tiny minute. Do it this way. Yeah, this is it, guys. See if you can get to here. Theta dot is equal to V over rho. See it? Theta dot's equal to V over rho. So what we got here is a V times V over rho U of n. And boy, Job, we have our equation now. If you didn't follow all that, that's okay. It's all based on the definition of what a derivative is and the arc length equation. I used the arc length equation twice, but here's the bottom line, and we'll be ready to work some problems. The bottom line is this. The acceleration in the normal tangential coordinate system is equal to there you have it. That's it. And you'll find those in the flap of your book. See, this is the tangential component. It says AT is equal to V dot. Boy, Jove, it's right there in the flap of your book where my finger is wiggling. And it says that AN, the normal component, is V squared over rho. And that's right there where my finger's wiggling there. It's in the flap of your book. Really, that's all you need to know. But it's kind of nice to have some idea where this came from. And now we're going to work some problems. The first problem I want to work is 12-134. It's on page 68. And help me find it. Page 68, 12-134, there it is. Motorcycle is traveling at a constant speed of blah, blah. Determine the magnitude of its acceleration when it's at point A. Okay, well, let's draw our axis here. And here comes this motorcycle. It's kind of going up a hill there. And this distance is 25 meters. And the motorcycle's right here. Artist's rendition of not very good. But we tried. We tried to put a motorcycle on there. There we go. Now the motorcycle's going kind of that away. I think the hill keeps going up. I don't know. Motorcycle's going up the hill. Now this hill has a, this is X and Y. This hill has an equation of Y squared equals 2X. And the motorcycle's going at a constant speed. The velocity of the motorcycle is 60 kilometers per hour. Okay, that's all we know. That's it, and they want the acceleration. Okay, well, how do you do that? Well, we could use this equation. What do you think? I kind of like it. Now the thing is, V dot is 0. You know what that is? That's the tangential acceleration. He's not accelerating tangentially. He's going at constant speed up this hill. He's not going faster and faster and faster or slowing down. He doesn't have the brakes on. The truth is he has to give it a little gas or he would slow down. But if he gives it just the right amount of gas, he can maintain the same speed up the hill. And see, that's speed, and the speed is constant. So his tangential acceleration is 0. But this is his normal acceleration. His normal acceleration is v squared over rho. Now we have his velocity. Now we might want to put that in meters per second. Here's how to do that. There's 1,000 meters in a kilometer. And there's, for every hour, there's 3,600 seconds. I don't know if we have to do that, but I'm going to anyway. We're going to figure out his meters per second. Here goes. 60 times 1,000 divided by 3,600. Did you get his velocity is 16 point blah, blah, blah meters per second. We've got his velocity. Look here. We've got his velocity. What does it mean in my class when you circle something? Well, it means we've got it. We know what it is. If we could only get this radius of curvature, we'd be done. Because this is 0. And if you could plug in this rho thing, you'd have the answer. We could be finished. Okay. How do you find the radius of curvature? Well, we have an equation for it. I talked about it. It's in the flap of your book. It goes like this. I talked about this Monday. If you didn't understand, go back and you watch that YouTube again of Monday. There's the equation. That equation is in the flap of your book. Let me show it to you. It's this equation right here where my finger is wiggling. It's right there. It's called the radius of curvature. See, this hill has a curvature, and we need it in this equation. Well, how do you find the dy dx? That's a good question. Huh? Well, we can do it. We took calculus. We're not scared by this. I need a little room to work here. I hate to erase all that wonderful hill there, but we got to find out. Why don't we? One way to do it that you might like the best is to say y is equal to the square root of 2 times x to the 1/2. Did I do that? Calculus students, did I do that right? Y is the square root of 2 times the x to the 1/2. I think that's right. What do you guys think? Okay, now we need this dy dx. Here goes. We're going to get dy dx. Here goes. Dy dx is equal to, wouldn't it be 1/2 times the square root of 2 times x to the minus 1/2? Did I do that right, calculus students? If I make a mistake, just speak up. Don't be embarrassed. But now we're going to need the second derivative. Let's see if we can do that. Second derivative will be, well, don't you have to multiply by minus 1/2? It'd be minus 1/2 times 1/2 times the square root of 2 times x to the minus 3/2. How'd I do it? I think that's right. Now we need to find the numerical value. Now they said x was 25 meters. I don't know if you remember, I erased it. Is that what they said? I lost my page. Let me look it back up again. Guys, in case you wondered what we're doing problem 12-134. We're doing problem 12-134 on page 68. And they said that you're at 25, x is 25. So we're going to plug in 25. Take the square root of 25. Square root of 25 times the square root of 2. Well, that'll give you y. I lost part of my picture here, but this is 7.071 meters is y, but I don't care about that. I want dy dx. All right, I'm going to plug in 25 to the negative 1/2, right? Times the square root of 2 divided by 2. Well, I got an answer. I got 0.14142. What are the units of dy dx? Anybody know? They're nothings. Dy dx is dimensionless. Now let's do this one. Now x is 25, so I'm going to take 25 to the negative 3/2. I can do that. Times the square root of 2 divided by 4. Only it's negative, isn't it? I'm getting a negative 0.00228. Uh-oh, ran out of room there. Hey, now I'm ready to find the radius of curvature. It's 1 plus 0.1414 squared. Wait a minute. That's wrong. Somebody could have gotten a thank you point. That's supposed to be to the 3/2. I made a mistake here, but nobody caught it. I need your help. It's 3/2. I got it right now. Now we're going to divide by 0.00. Well, it's negative, but when you take the absolute value, we don't care that it's negative. And this should give you the radius of curvature. And then we can get the answer. We'll be done. Okay, here goes. I'm getting 364.7 meters for the radius of curvature. I wonder if I did that right. I don't know. I could have easily made a mistake. But we're going to plug that in and we're going to get our answer now, because now we think we know what the radius of curvature is. So divide that number into v squared. What is v again? Oh, it's 16 point blah blah, but you have to square it. I'm getting a very small answer, 0.762 meters per second squared. Okay, let's look and see if I got that right by some miracle. This is problem 12-134. And I'm going to look in the back here. They have answers to a lot of these. And they said 12-134. They said 0.763. The answer book says 0.763. I got 0.762 meters per second squared. I think we did it right. Maybe someplace in here, maybe I didn't carry out enough decimals, or maybe they didn't. Maybe they rounded off too soon. But that's how you do that problem. Now we got time for one more problem. But before I do a different problem, I need to know about you guys. I need to know, are you just totally lost and don't have any idea, or you're just fine, you understand everything? Let me ask somebody. Let me ask my friend Shane. Shane, unmute and tell me how you doing. Did you follow this problem, this 12-134, Shane? He's on a coffee break. I think I just missed Shane. Shane, are you there? Earth calling Shane. Come in, Shane. Okay, well, let's try Ryan. Ryan, unmute and say hi. Ryan.
Oh, there we go. Hello.
Yeah, is that Ryan?
Yes.
Okay, now Ryan, are you totally lost, or did you follow this problem okay?
I followed you.
Yeah, good. Excellent. Excellent. We got to do some derivatives there. And we're using our equation here. Let's do another one. Okay, now this next problem that I want to do is 12-147. Let me make some room here. And we're going to do 12-147 now. We are going to do problem 12-147. 147. It's on page 70. Okay, now let me find it. Page 70. All right. I've got it here. Oh, 147. Okay, I see it. Jet plane traveling with a speed of 120 meters a second. Okay. Well, now let me draw the XY axis now. There's your XY axis. And this plane is doing this. It's going like that. And this distance right here is 80 meters from here to here. The plane is at point A down here. We'll put a little marker there where the plane is. This equation is y equals 15 natural log of x over 80. Okay. The jet plane is traveling with a speed of 120 meters a second. Okay, well, let me draw that. I'll put it in red. Here we go. See, here's his velocity. The velocity is 120 meters a second. All right. 120 meters a second. But it's decreasing. He's slowing down. See, what they're doing is they're giving us the v dot. The v dot is minus 40. You understand? He's not speeding up. He's giving us, you know what that is? That's AT. That's your tangential component of his velocity. His velocity is 120, but every second he slows down 40. So 1 second later, he'll be going 80 meters a second. You understand? He's slowing down. Okay, determine the acceleration when there, and then the direction of the flight. Well, we can do that. Okay, I think we got all the info there. All right. Now to find, I think they want to know this angle right here. See that angle? And they taught you this in calculus, I bet. See if this doesn't ring a bell. The derivative, dy dx, is equal to the tangent of that angle. They ever teach you that if that angle is theta, call that theta. Did they ever teach you that the first derivative is equal to the tangent of theta? Let me ask somebody. How about my friend Megan? Unmute. Megan, did they ever teach you that in calculus?
Yeah, I'm sure they did, but it's still rusty.
Yeah, I'm sure they did. I'm sure that I like the way you expressed that, Megan. Yeah. Well, let's do it. That's fine. They want to know that angle. We can do it. Here's the y, and we're going to take the derivative now. Instead of me doing everything, I mean, you can just sit there and fall asleep while I do everything. Why don't you do it? That'd be good for you. Character building. Look here. I'm going to shut up for 1.5 minutes or 2 minutes. And I want you to find the first derivative of dy with respect to x. We got the y. You took calculus. I need a number now, won't I? Yeah, I'll need a number. But go ahead. I'll shut up, and you have a couple of minutes. See if you can do that. why should I have all the fun? Yeah, see if you can do that. Find the first derivative with respect to x. Well, I don't know if that's 2 minutes or what, but let's go ahead and get this and let's compare, take a look at what you did and see if you did it right. Well, it's going to be 15 for sure. It's going to be 15. And now when you do the derivative of that, they taught me in school, just like you guys, I had to go to school. And I think it's 1 over that, which is x over 80. So far, so good. Isn't that right so far? That's what you do. You go 1 over that. Yeah. But you're not done yet, because you have to take the chain rule. You have to take the derivative of that. See if it had just been 15 natural log of x, and you took the derivative of it, you would get 15 times 1 over x, and you'd be done, see? But you don't just have x, you got x over 80. So you have to take the derivative of x over 80. Well, what's the derivative of x over 80? Well, I think it's 1 over 80, isn't it? Isn't that right? You have to take the derivative, you have to use the chain rule. Okay, now when you get done doing all this, I think what you get is 15 over x. Don't those 80s go bye-bye? All right, well, great. Now you can get the numerical value because x is 80. So see, if you plug in 80, you can get the value of dy dx. It is 0.1875. Now we're going to need the second derivative to get the radius of curvature. See, to get the radius of curvature, we're going to need this second derivative. Now, the first derivative is 15 over x. Maybe I should write that. We're taking the derivative of 15 over x. So let me write that. 15 x to the minus 1. See, we're trying to take the derivative of that. We're trying to take the derivative of 15 x to the minus 1. Well, I think it's minus 15 x to the minus 2. What do you think? Looks pretty good to me. Minus 15. Yeah, that's it. Now, if you want a numerical value, well, you got to plug in 80. X is 80, they said. See it? So what's minus 15 times, well, it's really divided by 80 squared, isn't it? Well, I get this weird number. I get minus 0.00234,375. I think that's right. Now, what are the units of that? I wonder what the units of that is. Did I do that right? I think I did. Now the units of this are nothings. So that what that must mean is that 15 has units of meters. And then when you divide by meters, you get meters over meters, that gives you nothings. But when you take the derivative of nothings and divide by meters, believe it or not, I think the units here are 1 over meters. If that's confusing to you, go talk to your calculus teacher. We don't really care. What we care about is finding the radius of curvature. So here goes. I need some room. How about up here? We need the radius of curvature. It's equal to 1 plus it's equal to 1 plus 0.1875 squared to the 3/2 divided by the absolute value of the second derivative. I know it's minus, but when you take the absolute value, you just get 0.00234, blah, 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 blah. Okay, let's get our radius of curvature. Here goes. Now, I need to find out if anybody out there is still awake and following along here. Shane. Seems like I tried to talk to you before, Shane, and I don't remember if we got together. Can you unmute and say hi? Unmute. Say hi, Shane. Uh-oh, coffee break. Taylor, unmute and say hi.
Hey, how's it going?
Terrific. Did you do this? I did it. What did you get, Taylor?
I actually haven't worked that out yet. I was just finished writing
That's
it down.
okay. Take your time. We're in no hurry. Let me pick on Tyler. Tyler, do you have this radius of curvature yet? See, I don't know if I did.
Yeah, I don't know if it's right. I
Yeah.
got 236.63.
That's not what I got. I could be wrong.
Let me retry it real
Let me
quick.
do it again here. You might be right and I might be wrong.
I got 449.4.
Well, that's what I got. I got 449.4 meters See, that's down here. Let me draw it for you. It's way the heck down here. If that's 80, then 449, that's 80, 160, 320. Man, it's way the heck down here. The radius of curvature. See, you can make a great big circle. And that's the radius of curvature. So now, now we can get the acceleration. There it goes. We know the tangential component. We're just going to write this out now. Radius of curve. We know the acceleration is equal to the tangential component plus the normal component. Well, the tangential component is minus 40. It's slowing down. And the normal component is v squared over rho. Well, what's a v? Oh, that's the 120. You have to square it, and you have to divide by rho, which is 449.4. Ta-da, and that's it. We just figured out the acceleration, but now I think they need the magnitude. So here, let's write it out, and we'll get the magnitude. Here we go. The acceleration is minus 40. You know, you could even write it like this in tangential normal components. Let me see what that is. 120 squared divided by 449.4. I'm getting 33.04. I think what they wanted was the magnitude. So you got to go 40 squared plus 33.04 squared. Let's do that. I wonder if I did anything right. I'm coming up with 51.9 meters per second squared. Let's look at the answer in the back and see. Let's see if we got what they think. We just tried to do problem 12-147. Okay.
Hey, I got 32.04, not 33.04.
Uh-oh, another wonderful person got 32.04?
Yes.
Uh-oh. Let me do that again. Let me try that again. 120 squared divided by 449.4. It's 32.04. This was wrong. Now tell me your name.
Alex.
Thank you, Alex. Thank you point goes up here in the corner for Alex. And I'm going to do this again and get a different answer. Here goes. We're going to do this again now. And I'm coming up with 51.3 meters per second squared. Now let's see what the answer book says. The answer book says those stinking bums, they didn't give us the they didn't give this answer. They did give theta though. They said theta is 10.6 degrees. For 147? Is that all? Well, what did we get for theta? Did we ever do the theta? I tell you what it would be. It would be your first derivative. If you take the arctangent of 0.1875, you should get that angle. Well, we'll do that. See what the arctangent is of 0.1875. Boy, Jove, it's 10.62 degrees. So they give that answer, but they did not give, they asked for the acceleration, I think. Let me go back and look. Determine the magnitude of the acceleration. Yeah, they asked for this, and we got it. And unless I made a goof with my calculator, we got the acceleration. But they didn't give the answer. Shame on them. But we worked our problem. Is there any comments or questions on that? Well, okay. Well, we've spent the day on the normal tangential coordinates. Let's review some things here. If it's okay, I'm going to erase all this jazz. Unless you have a question.
I think we're a little over on time now.
Oh, you know what? We are over on time. We're through. Dang it. We go from 9:30 to 10:50 thing. And who was that just spoke up?
That's Taylor.
Taylor, we're going to give you a thank you point, Taylor. You guys have homework. You're going to do the homework. We're going to say goodbye now. Thanks to Taylor. You guys can go do something else now because we're through. Goodbye, everybody.
Have a good day.
Bye.
Thank you.
I will.
Yeah.
Thanks.
Bye.